I changed the title a bit from what I had in the introduction, but anyway, what I'm talking about is modeling tools that make your life easier. So if you're going to build AI solutions that somehow require quantifying uncertainty, I'm here to help you, and much of FCAI is here to help you. This is definitely not a bureaucratic talk about what FCAI does, but I still want to show the one slide, meaning that we have a collection of research programs that do very high-level research on AI, addressing very specific questions that are currently bottlenecks in AI. And then we've selected already a couple of these kind of highlight demonstrators that we use to show for the rest of the world that we are doing good work. I talk about one of these, what we have to offer in terms of modeling tools that are easy to use. And the reason I talk about this is that for a fundamental research in methods, in AI, on any kind of computational methods, in order to have a societal impact, it has to be used by others. There need to be people in industry, in other fields of academia, using our tools. There need to be people that are solving grand challenges, like curing cancer, using our methods. Or there might be a slower route so that we first do something, then someone else brings that at the level where it has a practical impact. One of the big practical means of achieving this is delivering tools. Practical software, open source software that actually people start using and then start doing research with those. Here's one example from deep learning. We actually knew already roughly 20 years ago that how the core algorithms, how the model architectures of something like convolutional neural networks, how do they work? How should you train them? We still only saw the deep learning hype during the past maybe 10 years. And it's really, I would attribute much of it to the tools. So here's Google Trend TensorFlow was released around 2014. And this is just that I'm in the volume of that by Google Trends. Here's another illustration of the same phenomena. So they are aligned in time. Job listings that talk about neural networks. They go up pretty much exactly the same time. So the industry started to look for neural network people when it became easy to create those tools. We see the exact same happening on the scientific side. Neural networks have been a big thing always. But again, there is a very rapid rise, roughly around the same time, a bit later, of course. First you have the tools, and then you have a lot more research capability in the world for delivering these things. So in brief, what happens when we, as a community, are able to put out high-quality open-source tools, what we get is this virtuous cycle where people contribute to the same tools, everyone uses those tools, you have a lot more people working on this thing, so we come up with more and more new innovations, and then they are again put back to these same tools. Everyone believes and agrees with this, right? Good. I would say that this is the best example of an open source software success after Linux. What I'm talking about is probabilistic AI. So AI solutions that can properly handle uncertainty, which is extremely crucial when you don't have the kind of infinite amount of data that deep learning algorithms really build their success on. So when you have less data compared to the complexity of your model, what you need to do is that you really need to pay your attention to this uncertainty. You need to handle it properly. You need to express it explicitly. And you also want to be able to build as much of your knowledge of the problem that you're modeling into these tools. And this can be, of course, achieved by something we know as Bayesian statistics or Bayesian inference. You can work with kind of very simple interpretable models like linear regression, or you can work with extremely complex models, let's say deep neural networks, but you can still plug in Bayesian inference here to handle the uncertainty. The problem, of course, that this is not easy. We've known for decades roughly how to do these things, but it's actually very difficult to create models that are properly at handling the uncertainty. You need to be an expert in statistics. You often need to do this in a slow, iterative manner. You try out things. And often you need to kind of you go use tools that have very constrained, they are very limited because of some computationally simplifying assumptions. We wouldn't want to cope with those, but we have to in practice. Things have changed during the past few years in the same manner as things have changed with deep learning. There's something called probabilistic programming, which means tools that kind of transform the problem of building statistical models or Bayesian inference for any machine learning models into a programming task. You just express your modeling assumptions, then you push a button, automatic model-independent inference happens, hopefully correctly, usually rather well if the model is simple enough. And then you are really able to express any model that you want to using these kind of languages. So it is getting easier. So it's nowadays way, way, way easier to write a standard Bayesian model than it used to be like 10 years ago. But it's a fundamentally more difficult problem than deep learning, so it will take a bit more time. So here's just a simple example. So if you are willing to build some very simple statistical model, the way you express it in probabilistic programming is simply a piece of code, very nice for computer scientists, and then you get the result that properly quantifies the uncertainty in the parameters. So what FCAI is doing in this front is lots and lots and lots of research, just building to this whole idea of making it easier for you to build AI that takes kind of uncertainty into account. We're working on this kind of workflow of how should person build a Bayesian model, making it AI assisted. We're of course doing a lot of kind of fundamental research on individual steps of this kind of workflow, where you first start with data collection, then you iteratively build and validate the model and so on. We're working on model validation tools, inference techniques, really the hardcore inference techniques so that these actually work for complex models, how we can extract prior knowledge from the users, how we tie decision making into these inference problems and so on. And also talking about things like putting differential privacy as part of these software tools. Antti just talked about that a couple of weeks ago. Today, this is enough, everything I have to say about this general overall theme. I talk about this one particular problem inside this whole thing, which is called prior elicitation. So I need to go to a bit backwards and really actually define what I mean by the Bayesian modeling. So I'm talking about building a statistical model for a problem. You have some data, and then some unknown parameters that you would want to figure out based on some data that you have. We all know that this can be done with the Bayes rule. Conditional on the data, you have a probability distribution of the suitable values for these parameters. Importantly, it's still a probability distribution. We don't know that this particular set of values is the best. There is some uncertainty remaining because we had finite amount of data. To make this a bit more concrete, let's think about a specific model, like a Gaussian mixture model. Off-the-shelf standard machine learning algorithm. If we think about it as a Bayesian model, you just make some distributional assumptions, and in particular, you have some sort of parameter vector that tells for all of your Gaussian components the means and variances, and for all of your data points to which cluster they should be assigned to. The good thing about the Bayesian modeling is that there's a lot of places for us to encode our knowledge of the problem. Starting from the model structure, do I use a mixture model or maybe something like a latent Dirichlet allocation for modeling my problem? How do I assume my data generation to happen at the very level of the measurement? So what is the observation model? And then there's a lot of information on these prior distributions. So if I show here these examples, we had some prior distributions defining that what do we expect about our parameters before seeing any data. And this is what I talk about today. So how can we help the user to choose better prior distributions? To cope with that, I just introduce a bit more notation. I say that my prior distribution itself has some parameters. These are some sort of hyperparameters of our learning algorithm. Theta are the parameters that we want to fit into our data. Lambda are our hyperparameters that control what kind of information we are expressing before seeing any of the data. I use it to denote that by a parameter lambda, but I just note that it could also be a non-parametric distribution, as in non-parametric Bayesian statistics. But in most cases, it really is a parametric choice. So in our example of a Gaussian mixture model, we just have here in this case 5 different hyperparameters that somehow control what do we assume about the data before we actually see any data and before we fit the posterior. Now, why is this difficult? Well, there's 2 cases of what kind of models we want to build. One is that we are really building a hardcore statistical model. Maybe you're not a machine learning researcher, you are, let's say, a medical doctor who wants to build a specific problem that they know a lot about. They want to fit in a relatively simple model that describes maybe mechanistically what's happening inside a cell. The problem here is that even if for a statistician it would be easy to write down these assumptions, the person who has the domain knowledge usually is not an expert in statistics. And even if they were, it's actually very, very, very difficult to say how does a specific parameter here in hyperparameter controlling out my prior, how does it actually influence what my model is doing? These prior distributions can also be multivariate, so you have several of your parameters are being controlled by the same underlying prior. If you have a deeper model, some sort of hierarchical model, I may have a couple of unknown latent layers connecting this particular prior to your data distribution. And sometimes you even if your model is nicely interpretable, you may have some parameters that are not. So what we want to do is to help people do this properly, to really encode their prior knowledge as part of this model in a manner that is easier for them in technical terms. We also have another case. So if you think about highly parametric, very complex machine learning models, you can do Bayesian inference there. It actually makes a lot of sense. Even if you have a lot of data, if you have a very complex model, there is not much data for determining the specific parameters. Something like a Bayesian neural network, a deep learning model, or something like this, which is a already relatively old matrix factorization model expressed as a plate diagram. If you want to do Bayesian inference for these, you still write it as a collection of the kind of model structure and some prior distributions. But what people actually do in reality is that you don't try to think, what's my prior expectation about this and this parameter? Instead, they select these hyperparameters based on some sort of predictive accuracy. They do cross-validation, or they are simply lazy and say, I set all of my hyperparameters to 1. This is what is happening. It's kind of strictly incorrect from the perspective of Bayesian statistical kind of philosophy, but it also, people do it. We need to have tools that help them. So what I want to offer is things that make it faster in a somehow of automatic manner to select what these hyperparameters should be, instead of doing something like computationally extremely heavy cross-validation. Scales exponentially in the number of parameters that you're interested in. The tool that I have to offer for this is something called prior predictive distribution. So it is actually this is the Bayes rule. What is the posterior distribution of the parameters given the data? It has this normalizing constant, this marginal likelihood, terribly difficult to compute. It's an integral over all of our parameters, possibly millions of them in some sort of a complicated model. And it's really a nuisance. We don't really want to play around with that. But in this case, it actually turns out to be useful. We can do all of these tricks exactly because we formulated our model as a Bayesian problem. If you just look at this quantity, it's actually what it's telling is that it's integrating out all the actual model parameters. It's telling us what to expect about the data conditional on the hyperparameters we had. And it's been used already in Bayesian statistics. It's used for something called prior predictive checks. If you're building a model, you're advised every now and then to check what would my data look like if I sampled data, these parameters from my prior and then sampled the data from here. If it's completely off, the recommended practice is to change your priors. Our idea is that we go further. Based on the prior predictive checks, we already know that the predictive distribution that marginalizes out the parameters should be roughly comparable to what you actually expect about the data. What we do is that we make this into a practical operational procedure. We learn prior distributions such that some simple summaries of the predictive distribution correspond to our expectations about the data. Or in the case of this black box machine learning approach, that actually match the statistics that we compute for the observed data. Here's an example. This is some data that I've collected, follows some simple Poisson-looking distribution. It's just a histogram of a univariate variable. And I've already marked here some statistics. The mean of this distribution is around 7. The standard deviation, I'm just marking it here, it's kind of also around 7, or a bit less, whatever, it's 5. I don't know what it's the actual number here. This is my data. These are some statistics of my data that I would want to capture with my prior predictive distribution. Here's an example of 3 particular choices for my 2 hyperparameters in this model that control some specific gamma distribution priors in my model. And here are density plots of the prior predictive distribution obtained by sampling from this distribution. And we see that for hyperparameter values that are very close to each other, almost 1, you actually get very different predictive distributions. The red one matches roughly the mean that we had in this actual real observed data. Also, it actually matches the variance relatively well. Whereas let's say the black one, that is kind of innocently looking relatively close to that, it still overestimates by roughly a factor of 2. It really doesn't match your actual data in any reasonable manner. So this is the idea. What we would want to do is that given this knowledge of these statistics, we would want to find out this red prior distribution that roughly corresponds to the same statistics. Of course, the practical problem is that we don't know how to do this. The prior predictive distribution, it's the nasty thing that we don't know how to compute. But luckily, we can still build practical algorithms around it. I showed today some concrete examples building on 2 unpublished papers, things that we just submitted 2 weeks ago. In one of them, we used the knowledge that there are models for which we can actually compute expectations of the prior predictive distribution in closed form. And we can still do this learning even though we don't know the distribution itself. And then in the other paper, we also use this kind of, we can always sample from this distribution. We sample first the value for the parameters from this prior distribution, and then we sample the data. So we can build practical algorithms based on that. So let's get back to these actual real cases. I start with this case of wanting to build an interpretable model where there is this medical doctor building a model that they really want to do about. So this is really work by Marcelo Hartmann and Georgi Agiashvili about prior predictive elicitation. Talks about the knowledge elicitation, so the procedure that we want to help an expert to expertise knowledge about what they know about this problem and turn it into a prior distribution that somehow encodes their subjective knowledge. And what you do is there are procedures for this. People have been building interfaces. You ask questions about the prior distributions. Do you believe this and this parameter should be larger than 10 or not? What should be the variance of this parameter? This is actually very, very hard. If we move into using this prior predictive distribution, what we get to do is that we get to ask questions about the data itself. Not about the parameters, but we can ask, do you expect this observed number here, which is, let's say, the blood pressure of an individual, do you expect that to be roughly 100 or roughly 1 million? Every single doctor and probably everyone in the audience already could answer that. So you don't need to think in terms of these complex distributions, you really think about in terms of observable quantities. This is not a new idea. It really has been around for some decades, but there's lack of practical tools that actually model this properly. What we proposed is a technique that you essentially kind of express your model in arbitrary probabilistic program. You just leave the priors kind of unspecified. Then we ask questions from the expert about the observed data itself. What do you expect the probability distribution of this and this variable to be? We model these as noisy observations of an underlying Dirichlet model and then try to really optimize for the hyperparameters such that the prior predictive distribution matches these noisy observations that the expert provided. I don't go into any of these details. The paper is not really out yet. You can ask me or Marcelo to send you a copy if you want to read about the technical details. It's based on sampling from the prior predictive distribution. We use simple off-the-shelf black box kind of optimization algorithms here. We're working in a very low dimensional space of only a few hyperparameters, so it actually turns out to work very well. What we can do compared to what was around earlier is that we can handle multimodal priors. We can handle multivariate prior distributions just as easily as if the prior was a simple univariate thing. The earlier techniques could only more or less handle that. Then let's switch to the other case of complex machine learning models that you still want to do Bayesian inference about. This is based on Eliezer da Souza da Silva, Thomas Kuzmiecik, Marcelo Hartmann, and me, submitted to the same conference as the previous one. I think it was submitted to arXiv yesterday, so the paper should be out today or tomorrow. So what we really talk about is that you build two-stage Bayesian modeling here. You don't really care about your prior distributions in a kind of philosophical sense of how do they encode your information. You just want to pick good values so that your model works well. You might not even care about the posterior distribution. It's just a regularization technique. And what people do, of course, is that you do some sort of a cross-validation or, let's say, Bayesian optimization for choosing these values. And the critical problem here is that when you do that, you constantly need to be doing the actual inference, Markov chain, Monte Carlo, variational inference, whatever you decide to do. For any given choice of hyperparameter values that you want to test, you need to do this. It takes a lot of time. With the prior predictive distribution, we can do it without computing the inference at all during this procedure. Of course, at the end, we still want to do the inference once with the hyperparameter values that we chose. So what you can do is, essentially, this is an extract from our paper. Don't read that now. What you just do is that you select some simple statistics about your data, ask them from the user, or even just measure them from the data, some sort of separate validation set if you wish. Then you solve for your hyperparameter values such that the prior predictive distribution corresponds to your expected statistics. And once you've done that, in the end, just once, you'll do the actual posterior inference. A practical example, Poisson matrix factorization. So you have some count-valued data matrix that you want to learn a low-rank approximation, useful, for example, for recommender engines. Here's just the expression that you have a Poisson likelihood and then some prior distributions. We're not fixing even the parametric family of these prior distributions. It's just some location scale family of priors. What it turns out that for this specific model, we can compute the mean, variance, and then some correlations of how much we expect different elements on the same row or column, to how strong is the correlation between those. We can compute these in closed form. We just get expressions like this. The correlation along one row is this kind of a bit nasty looking expression, but it can be still written. It was 11 pages of supplementary material in that paper just for these derivations, but it can be done. What it means is that once, because we express them in closed form, we can also solve in closed form for the optimal prior parameters, these hyperparameters, so that it matches these statistics. In particular, we get, as a practical example, we can solve for the optimal number of factors for Poisson matrix factorization in closed form as a function of some of the statistics of your data. For Poisson matrix factorization, also for slightly more broader family of compound Poisson matrix factorization. So that really kind of solves the eternal question of how many factors do I need for a matrix factorization for this specific model. It works. So here's the kind of true number of factors. Here's the estimated one. And this happens for free. There's no computation needed. You just solve these analytically in closed form. And if you eventually do posterior inference with your chosen K, it's almost optimal in terms of the predictive accuracy of your model. Of course, the problem here is it's ridiculously tedious. Like I said, it's 11-page supplement doing all of these derivations. And slightly more complex model, you almost certainly could not do it. What we do in the other half of the same paper is propose a general model-independent approach based on doing this same thing. That is simply sampling based on kind of stochastic algorithms. You sample from the prior predictive distribution. You use Monte Carlo integration for computing these expectations, and then you backpropagate gradients with the reparameterization technique. Again, I don't talk about the details. They are there in a paper, and this one really should be out today. Read the things. We cannot handle discrete hyperparameters as of now, so we don't actually get, for example, this optimal number of factors that we got in these closed-form solutions. The critical thing here is that as an optimization problem, we are working on a very low-dimensional problem. Just a few hyperparameters in most of these cases. And something that I also wanted to mention, that if in case you started wondering, it actually is very close to kind of simulator-based inference algorithms that are also studied extensively in FCAI. The core difference being that we don't care about the posterior of the hyperparameters. We actually really just want to get some simple values here. Some illustrations from the paper. It does work. So we can, for example, solve this Poisson matrix factorization case, which we did in closed form. With this algorithm as well, we get the exact same solution. We can also show that, for example, you could have such statistics in your observed data that it's impossible to reach it within a given model family. That's kind of an indication of that maybe your model family is not really the right one for this problem. With this, I would like to conclude just by 3 things that you need to remember about today. Bayesian statistics is the right tool for handling uncertainty, and you always need it. It's advertised as something you need for small data, but all the time when you get more and more data, you want to switch to more complex models to answer more complex questions. So the need for that never gets around. Probabilistic programming, if you did not yet hear about that before this talk, now you should remember this. This is the default go-to tool for building especially interpretable statistical models. And what we are doing at FCAI is thinking about all possible ways of making it easier for you to build your probabilistic AI models. And then I talked about this very specific technical contribution of how we can use prior predictive distribution to help setting optimal priors for our models, both in the case of these interpretable models where we really ask questions from the experts, and in the case of kind of black box machine learning modeling where you just want to get good or reasonably good hyperparameter values for your model without computationally expensive cross-validation or other techniques. Thank you.
So if you are able to choose the number of components, the K, in one of these examples, have you checked that, does that correspond to some of the standard model complexity selection?
No, we have not really checked that. So the only verification we've done is those kind of on artificial data where we know the true answer, it actually retrieves that. And then if you go and do posterior inference, it's reasonably good. It almost certainly does not exactly map to any of the existing. For example, here, what it really uses as an input is not just the mean and variance, it really builds on the expected correlation of these. So it really, I think it uses different sufficient statistics of the data compared to any of the standard techniques. So, But it would be an interesting question of whether it's in the same ballpark if you really do it.
Right, and also,
Yeah.
I mean, if this is not the same, could you propose this as one?
Yes. Yeah, I think possibly. Yeah. Yeah.
Okay, thanks also for an interesting talk. What I would like for you to answer is that what's the difference between these? You say that you use the data, you use summary statistics from the data, or then a subset of the data.
Yeah.
So how does this like align with empirical Bayes or approximate Bayes? It seems that this is empirical approximate Bayes.
This is empirical Bayes, yes. The philosophical motivation is the same, that there are some parameters for which you're willing to set point estimates by actually looking at your data in some reasonable manner. I think so in practical things, what we really want to do here is that I'm willing to step outside the formal Bayesian procedure for a while to do these simplifying choices here as I would in empirical Bayes, as long as I don't really use too much of my data to already specify my prior. So for example, in the matrix factorization case, this is learned based on means, variances, and correlations. So it's actually enough to look at one entry of your matrix and see what's the expected value of this. All of the actual structure in the data. So what is that's kind of still unused, and you can do reasonable posterior inference with that. So I think this is where we are. The approximate Bayesian computation, I think the connection is a bit looser in a sense. We have similar technical algorithms because we use sampling from the prior predictive distribution. But we're not really looking for Bayesian inference over these lambda parameters. We are really happy to choose one, and we claim that this encodes the knowledge we have about the parameters. Yeah.
This is the same question again, you say it is. But it seems to me that so you predict certain statistics about the data, in this case mean variance and covariance. But this could be, if I've understood correctly, quite sensitive to which statistics you use.
Certainly, yes.
Directly from the model, or how does a non-expert know what statistics are appropriate?
Yes, that's a very good question. So the richness of these statistics, of course, determines how close this gets to the, let's say, actual posterior inference. If you used as statistics all of your data, this essentially reverts back to just doing standard inference. In practice, what we've tried out are very low order moments. So we haven't even played around with anything that goes above using the variance. So I think the basic idea is that all the kind of simple statistics that you could realistically be able to express, or in this particular case, all the statistics that we are able to compute in closed form. Trying to do this for any higher order statistics in closed formats, I think it's another 20 pages of derivation. And I think there is a risk if you fit this prior to too rich set of statistics, you're already kind of stepping a bit too far maybe in terms of looking at the data twice. Yeah.
Any further questions?
No?
Yeah, then let's thank